it's 1 o'clock, we probably we just have to start because we have some material to cover. Okay, so the final exam is on Monday at 12:30 here in this room. For people that are registered for this section, this is probably the best day for the final exam because well, Monday you're done for this week physics. Now, here are some material, some problems from the old material that is going to be on the final exam in some modified form. I'm only talking about calculational problems. All conceptual questions during the semester that we have encountered in practice tests or homework assignments are going to be, some of them are you're going to see again, in some version, maybe slightly modified. But for the calculational problems from the old material, review the following questions. From practice test for midterm 2 practice. Problems 15, 18, 19, so problem 15 is Faraday's law of induction, very simple. 18 is RCL circuit. You need to know impedance and inductive capacitive reactance. And problem 19 reminds you that magnetic fields are generated by currents and magnetic fields are vectors. From midterm 3 practice. Review the following questions. Problem number 15 and problem number 17. So problem number 15 is there. What was it? It was about given the intensity of light, figure out the energy carried by this electromagnetic wave in a certain amount of time, and figure out what is the RMS value of electric field, magnetic field, maximum RMS value. We had questions like that in the last midterm. So this is problem number 15, and problem number 17, I don't remember what it was, but again, it's a problem that we have solved. You're going to have, 17 is probably a problem related with near point, far point, correction of the vision. So in this type of problems, it is very important to have a descent diagram to show the distance dO, the distance di, together with their algebraic sign. Those things have to be, the diagram itself is worth points. It is, without it, the solution is a little bit very easy to mess it up. So you can add here problems related with eyeglasses, contact lenses like this, right? And another problem that is easy, but you have to figure out how it works, is homework 24, problem 16. So I think it was a problem where you had a cell phone and they're asking you how much energy this cell phone transmits through a window with certain area. So again, it is a problem similar to problems from the midterm to practice test, but I can modify a problem like this by asking also what is the RMS value of the electric field, what is the peak value of the electric field, the magnetic field, RMS and peak value. So those are the problems that you have to review for the final exam, calculational problems. In addition to that, from the new material, you're definitely going to have a question about resolving power, either of a human eye or some telescope or some other optical instrument. So this is chapter 27. The homework assignment, we had questions of that type. This is something that you're going to get from the new material. And from the new material, you're also going to get conceptual questions similar to those in the homework assignment on the last 3 chapters. And you're going to have a question about carbon dating. Or in general, radioactive isotope dating in general, similar to the questions that are in the homework assignment. The homework assignment that is due tonight. Okay, any questions? Oh, the formula to calculate your semester grade. So the formula is going to look like this. Your final exam score divided by the total final exam. So maybe the final exam may have, I don't know, 120, 150 points. So whatever is your score divided by this, by the total, with a weight of 38%. The two highest midterms with a weight of 35%. Your homework, total homework, divided by the total available homework points with a weight of 25%. And fill those brownie points Google Doc for an extra 2%. So this expression multiplied by 100, and the points that you get are going to tell you if you're going to end the semester with an A minus, B, and so on. So the table which percentage that you need in order to get certain letter grade are listed in the syllabus. So I'm going to post immediately after I have the grades, final exam grades, I'm going to post them on WebAssign. And using this formula, you can calculate what your semester grade is going to be. Okay, questions? Okay, so the grading is, there is no curve fitting for the grading. So if everybody does well, everybody gets an A for the semester. Now, if you get a grade of 90% or higher on the final exam, this formula is not valid In that case, automatically you finish the semester with A or A minus. 90% of the final, A or A minus automatically, no other discussions. Okay. If questions, anybody? Any? Yes.
So there won't be a practice test for either of those?
We don't have time for practice test, and this is good for you because for the last 3 chapters, the new chapters that we covered, you have homework assignments, and therefore the problems are going to be a version of the homework assignment problems. So and the homework assignments for the last 2 chapters are very short. They are not very difficult to solve. Okay. Well, if you don't have other questions, let's talk a little bit about radioactivity and its applications for practical cases. So we have very simple detectors that are able to detect the presence of radioactive materials, like this Geiger counter. So we said that last time we classified the types of radioactivity as alpha, beta, or gamma. So some nuclei prefer to decay via emission of an alpha particle. Alpha particle is a helium nucleus, and this type of decay reduces the atomic mass by 4 units and reduces the atomic number by 2 units. The beta type of radioactivity is an emission of an electron and neutrino, antineutrino, electron and antineutrino. And it increases the atomic number of the radioactive element by 1 unit and keeps the atomic mass unchanged. So this is for beta minus radioactivity. And finally, you have gamma type of radioactivity, which is an emission of a photon from a radioactive excited nucleus. This type of radioactivity doesn't change the atomic number or the atomic mass of the nucleus. So different radioactive elements may decay via 1 or more than 1 decay channels, one of those. So you have elements that are alpha and beta and gamma radioactive with different probability of decay in one of those channels. Now, the radioactive decays are probabilistic. So if you look at some sample of radioactive materials, you cannot predict when some nucleus is going to decay with certainty. But on average, you know that for certain type of radioactive materials, on average, you have certain number of radioactive decays of any type per second. So for example, here with the Geiger counter, when I turn it on, each beep corresponds to 1, usually either gamma or beta particle going through the sensitive volume of this counter. So the beeps that you hear now are due to the radioactive background, mostly due to potassium-40 present in this room, in the walls, and also due to cosmic rays. Now, when you get close to material that contains radioactive nuclei, you see that the detector starts detecting at much higher rate. Each beep is one disintegration of a radioactive nucleus in the material. Here. Now, there are detectors that are more sophisticated, and they can tell you almost with 100% certainty if a particular decay, if a particular beep is due to uranium or thorium or potassium or to whatever element it is. With almost 100% accuracy, it can tell you what is the original decay nucleus. Well, the number of beeps that you hear per second is called activity. So activity defined as number of beeps per second, but again, each beep corresponds to one disintegration, to the change of the number of the radioactive atoms by 1 unit. So if you start with a sample, let's say that at a certain moment of time has 100 radioactive nuclei, and if after, let's say, 10 minutes, you have heard 10 beeps, therefore you had 10 disintegrations, the remaining nuclei that are still not decayed is going to be 90, 10 decayed. So you can say that the number of decays, of radioactive decays, is the change of the number of the radioactive nuclei that you have in the sample. And that change is negative because you go from 100 available to 90 available. And usually by delta, we think about final minus initial. Final is 90, initial is 100, delta n is a negative number, negative 10. So this number of disintegrations per unit time is what is our definition for activity. The SI unit for activity is becquerel. 1 becquerel is 1 disintegration per second. But you have a number of alternative units that are in use. For example, 1 curie is approximately 3.7 times 10 to the 10th becquerels. And this is the activity of 1 gram of pure radium. But becquerel is the SI unit, SI system of unit preferred unit, and this is what we're going to use in this chapter. Well, the number of disintegrations that you can observe should be proportional to the amount of available radioactive nuclei, right? To the number of available radioactive nuclei. Therefore, delta n has to be proportional to the number of available nuclei. And of course, you're going to have larger number of disintegrations if you observe for longer time. But per unit time, you have a number of disintegrations proportional to the number of radioactive nuclei in your sample. The coefficient of proportionality is a number specific for the type of the radioactive nuclei. And that coefficient of proportionality is called decay constant and denoted with the Greek letter lambda. Now, since delta n is a negative number, n is number of atoms, so it cannot be negative. In order to work with positive decay constants, you insert a negative algebraic sign. So the activity of any sample is proportional to the number of nuclei in this sample times the decay constant with negative algebraic sign in it. Again, the decay constant is a number specific for different radioactive nuclei, and you're going to see the minute that it has a dimension of inverse time. From this expression, with a simple calculus, you can demonstrate that the number of remaining not disintegrated radioactive nuclei at some moment of time t is equal to the number of the available radioactive nuclei at the initial moment of time, whatever that initial moment of time is for you, times e to negative lambda multiplied by the time between the initial moment of time and the moment of time you're counting the remaining radioactive nuclei. So n as a function of time. This is the notation that I'm using right here. This formula is not proved, but it is a basic result following from this one using simple calculus. Now, if you multiply and divide, well, if you modify a little bit this expression in order to get a ratio of this type to both sides of this equation, you can very easily convince yourself, and I'm not going to do the arithmetic, that the activity at some moment of time of your sample is equal to the earlier activity at time 0, let's say, times the same exponent t to negative lambda multiplied by t. So the activity, just like the number of radioactive nuclei drops exponentially with time, the activity of any sample of radioactive material also exponentially drops. Here, the decay constant from this expression, it is clear that the decay constant has to be measured in inverse time, inverse seconds or inverse other time units. Well, we said that the decay constant is different for different materials, for different radioactive materials, but usually people don't tell you, people don't tabulate usually the decay constant of different nuclei. Instead, they're talking about half-life time of some radioactive material. Half-life time is defined as the time interval in which the activity of your material drops by a factor of 2. So half-life time, one notation for half-life time is T1/2. And from the definition for T1/2, let's say applied to this formula for the exponential drop of the available radioactive nuclei, you can say, well, at certain moment of time, my available radioactive nuclei drops by a factor of 2, while initially it was n naught. And this happens if the time is exactly one half lifetime, lifetime of this particular material. So this expression is the definition for T1 half. And from this expression, it is not difficult to find the connection between the decay constant lambda and T1 half. Let's do it. So you see that you can cancel immediately the number of your radioactive materials initial in the sample. And the result is going to be 1/2 is equal to e to negative lambda T1 half. Next, you take a logarithm, natural logarithm of both sides of this equation. So logarithm of 1/2 should be, and you use the following properties of the logarithms. Logarithm, natural logarithm of e to any power beta is exactly equal to that power. In other words, natural logarithm of this exponent is exactly equal to negative lambda times T1 half. Also, recall that logarithm of a to power b is b times logarithm of a. This 1/2, you can think about this 1/2 as 2 to power minus 1, right? Logarithm of 2 to power minus 1 is negative lambda T1 half. And this minus 1 can come in front of the logarithm, and you're going to have negative logarithm of 2 is equal to negative lambda times T1 half. And you can cancel the negative sign from both sides of this equation, and you get the result that we wanted. You get that half-life time is equal to logarithm of 2 divided by the value of the decay constant. In other words, half-life time, logarithm of 2 is 0.693, and so on. So this is a useful expression that allows you, given the decay constant, you to find the half-life time, or vice versa. Given half-life time, you to know the decay constant of your radioactive nuclear material. Okay, let's see questions and remarks. Now, to solve problems from this chapter, you probably need the definition for activity in this way, let's say. Here's the definition, and here is the introduction of the decay constant. And you need to know that the materials decay exponentially with those two, one of those two, their equivalent formulas. And of course, you need to know the connection between T1 half and lambda. So as examples, let's look at problem number. Let me start with problem number 6 from the homework assignment, because it is very similar to problem number 7. So problem number 6 from the homework assignment. Yes.
What does it mean when something is 7D? Is it like bigger than 3D, I guess? Because there's 7D on that, and there's a 7D plate according to the foam on the desk.
Oh, this is a very secret code. It tells you where this particular item is located on which shelf it is in that room.
I thought it was a special kind of glass or something.
It is very special code for location, for finding the things easier. So there are many toys in this demo room behind us. And sometimes it's difficult to find a particular toy. So this is why this is. But now let's go to carbon dating. So they tell you that you have to mention material. It has to be material from live object, a piece of wood or something. And they tell you that it contains 1 gram of carbon. And when you measure the activity of this 1 gram of carbon, you see 0.17, 0.178 disintegrations per second in 1 gram of your material. They're asking you how old is this piece of carbon of lumber or whatever it is, whatever sample you have, how old it is. So now look, carbon dating is based on the following fact. The natural carbon around us is stable. It is not radioactive, carbon-12. However, you have a radioactive carbon-14 that is constantly produced in the atmosphere due to the interactions of high energy cosmic rays with nitrogen atoms, with nitrogen nuclei. So you have constant production of carbon-14. And simultaneously, those produced carbon-14 nuclei decay with half-life time of 5,730 years. So at any moment of time, you have some equilibrium concentration of carbon-14 in the atmosphere. And since the chemical properties of carbon-14 are identical to the chemical properties of carbon-12, normal carbon, living organisms constantly absorb, together with their food, they constantly absorb carbon-14. Plants, animals, all of them have equilibrium concentration of carbon-14 in them, because this is it is coming from the plants that they eat, from the soil, for the case of trees, for example. But you need to know a few things about this carbon-14. First, the half-life time, it is 5,730. It is going to be given, of course, on the final exam. And you also need to know this equilibrium concentration of carbon-14 in objects that are alive, in the human body, in a piece of wood that is still alive, in a piece of some plant material that is still alive. The equilibrium concentration in 1 gram of carbon containing sample is 0.23 becquerels of activity for every gram of carbon. So every gram of carbon in a live sample provides you activity of 0.23 becquerel. This is when the sample is alive. At the moment when the object dies, its metabolism stops and the influx of new carbon-14 atoms stops. And therefore, you have this exponential decay of carbon-14 according to this expression or this expression there, identical. So in the problem, they tell you if this is the A naught, the equilibrium activity of a live sample, they say that your sample has activity A. It is, for my version, it is 0.178 becquerels per gram, per 1 gram of carbon in your sample. Well, now, once you realize the meaning of those numbers, this number has to be, well, not memorized, but it is going to be provided because it is needed for if you have a question about carbon dating. You can use this exponential decay formula, and that exponential decay formula tells you A is A naught e to negative lambda t. In other words, the ratio of current activity to the activity of a live sample is e to negative lambda t. Again, take logarithm of both sides of this expression, natural logarithm of both sides. You're going to have natural logarithm of this ratio is equal to negative decay constant multiplied by time. And therefore, solving for time, you have the age of your sample is equal to negative 1 over lambda times logarithm of the ratio. Now, of course, you can say, well, what is the decay constant lambda of carbon-14? And I just erased the formula, which says that the decay constant of any material is related with half-life time via 0.693 divided by the decay constant. So they give you the half-life time of carbon-14. From there, you can say the K constant or its inverse is equal to T1/2 divided by 0.693, for example. Substitute that here, and therefore you have that the age of your sample is equal to negative half-life time divided by 0.693 and multiplied by the ratio of the activities. And this should be the answer. If you enter the half-life time in years, the age of your sample is going to appear also in years. So notice that the logarithm is going to be a negative number because the ratio of those two activities is a number smaller than 1. So this is a negative number with this minus sign. The result becomes positive for the sample. See questions and remarks? Okay, so problem number 7 is very similar. problem number 7 is practically identical. The only difference is that they don't give you the activity of 1 gram of sample containing 1 gram of carbon. They give you the activity of a sample that contains 10.2 grams of carbon. So what do you have to do? You just have to say, my current activity is not 1.4 becquerels, but my current activity is 1.4 divided by 10.2. This is the only difference. Because you need to know the activity of a sample that contains 1 gram of carbon, not 10.2 grams. So just substitute the numbers, and instead of 0.178, use the number 1.4 divided by 10.2, whatever that number is. And you're going to get, again. So usually, look, if your sample, let's say of wood, is very old, let's say if it is 100,000 years old sample, maybe some already carbonized sample of wood, carbon dating is not going to work very well, because in 5,730 years, you lose half of your radioactive carbon 14 atoms. Another 5,300 years, 700 years, you lose another half, and so on. So in something like 100,000 years, you have 20 times reduction of 1/2, and your sample is going to have such a small amount of left over carbon 14 atoms that you probably won't be able to see, to detect their activity. So carbon dating works well for samples that are younger than something like 50, 60,000 years. But 50, 60,000 years in many cases, especially for dating related with some historical artifacts, usually it is completely relevant. Okay. Any remarks or questions on this? So problem number 8, the last homework problem in this chapter in this semester is about dating of a geological sample, rock specimen. So look, I gave this problem intentionally because I was shocked when a young person about your age started arguing with me that there is no way to know that the Earth is 4.5 billion years old rather than 6,000 years. There is no way for people to know that. Actually, there is. And studying rock specimens, and especially the isotope ratio of different radioactive isotopes in a rock specimen, gives you a very good measurement of the age of the sample. And from this type of questions, you practically determine, well, you can argue, is the planet 4.4 billion years old or 4.3, or you can argue about small details, but it is certain that the planet is more than 6,000 years old. We have actually historical artifacts, human artifacts that are older than that. Now, how does this work in the figuring out the age of some geological structure. Look, originally the planet, in the process of formation, the gravity pulled together dust and gas from the original nebula. When the gravity pulled them together, the protoplanet had high temperature because of the gravitational pull of pieces of rock and pieces of dust. Bringing them together with high speed, they collide, they are hot. So that the minerals were not in solid state, but they were lava, they were melted rock initially. Gradually, the temperature of this melted material dropped, and with formation of usually crystal structure. But those crystal structures, those crystal lattices, contain radioactive materials, for example, uranium-238. So at the moment of formation, the uranium atoms started disintegrating via alpha decay, let's say, generating, so alpha decay of uranium-238 gives you thorium-234. Studying the ratio of uranium-238 activity due to uranium-238 to activity due to the radioactive thorium-234 gives you exactly the ratio that they tell you here. 67% of the original uranium content is left, which means that 32.5% are converted into thorium, let's say. And you can measure exactly that ratio, and this is how this number is measured. And therefore, once you have this number, the rest is easy. Because, yeah, we're almost done. You are practically told that the current number of uranium atom divided by the original number is exactly 0.67, right? 675. This is what 67.5% is. This is this ratio. But look at the exponential decay formula. N divided by N naught is also equal to e to negative lambda times the age of the sample T. Taking logarithm of both sides of this equation, you're going to get natural logarithm of 0.675, let's say, is equal to negative lambda times T. And therefore, the age of the sample is equal to negative 1 over lambda times logarithm of 0.675 for my version of the problem. Again, the inverse of the decay constant is the half-life time. In other words, the age of your sample in terms of half-life time is whatever the half-life time is with minus sign and divided by 0.693 times logarithm of 0.675. And this should be your answer. So natural logarithm of 0.675 is a negative number with this negative sign they cancel out, and you get the age of the sample. So for my version, the number that you have to get is 2.53 billion years. So it is really very old rock formation. So probably some of the oldest rock formation geologically are about this age, about this. They're quite rare, by the way. Okay, any remarks and questions? If not, I'll see you on Monday. Thank you for your patience and your hard work this semester. And hopefully everybody is going to finish the semester with an A. This is the goal, right? Okay.